All right, we're going to talk about Munk's Abyssal Recipes. It's based on a paper by Walter Munk in 1966, and it's a very simple model explaining the overturning of the global circulation. So it's a simple parameterization. So the picture to have in your mind is a cross-section of the ocean like this, with the equator in the middle, the high latitudes at the extremes, and this is the sea surface, so it's a cross-section. And what you can imagine is that if in the wintertime, the high latitude water will be warmer than the atmosphere, and so you'll have a net loss of heat to the atmosphere, so there'll be a flux of heat outward out of the ocean at the high latitudes. And this outward flux of heat is going to cause the water to cool. If the water cools, it will get dense, and if it becomes denser than the water below, it'll sink to the bottom of the ocean. And another process that also happens at high latitudes in the wintertime is you lose heat. You also form sea ice. When the ice forms, the salt is left behind. And if the water then melts, is blown away, not the water, but if the sea ice is blown away from where it forms, so if it blows away from the edge of the ocean, the continent, then when you form the ice, you leave behind the salt water. The ice is transported away and melts further away, so there's a net transport of fresh water, which acts to concentrate salt. And the increase in salinity causes the water to be denser, and that also will cause it to sink and convect to the bottom. Now, so this, you have this kind of picture where the water flows downward, the cold water forms, and it fills up the bottom, the abyssal ocean. Now, if that's all that was going on, that cold water would fill in and it would start pushing up, and the whole ocean would fill up with this very cold and saltier water. And eventually, the water at depth would be equal to the maximum density that you reach as the surface in high latitudes in the wintertime. And then even though you would cool down at the surface in the winter, the water will not get dense enough to overturn. And so you just end up with a very shallow circulation, just at the very top of the ocean. So you'd have heat coming in and the water would flow north as it cools, but it would not sink down. So you'd have it overturning, it'd be very shallow. If you want to have a global overturning that goes all the way to the bottom, there has to be some way to take the heat that is lost in high latitude and put it back in the deep water, so that when you cool in the winter at high latitudes, you become denser than below, and then you can convect. And the physical process that causes this is turbulent mixing in the ocean. So waves will break, and when they break, they mix. So you can imagine if you go to the beach and you see the surf, when it reaches the shore, the waves get very steep and they overturn, and in the process there's a lot of churning and mixing. Well, something analogous happens in the interior of the ocean. You will have maybe tides generating waves, so as the tidal currents slosh back and forth, if they go up and over some topography in the bottom of the ocean, this will excite some waves. The waves will not propagate at the surface, you won't see them, they'll propagate on density interfaces in the interior of the ocean, because remember it's stratified. If the water is stratified, then you can have waves, and the restoring force, if you pull up denser water, gravity will want to pull it back down, and it will oscillate. And those waves will also break on steep bathymetry along the edges or close to seamounts. And the net effect is to cause some turbulent mixing that allows the heat that is put in at the surface in low latitude to be mixed downwards into the bottom of the ocean. So that balance between the deep water filling up with the deep ocean filling up with cold water, flowing upwards, and then downward diffusion of heat, that is basically Munk's Abyssal Recipe. So it's a one-dimensional picture that represents sort of the large-scale integrated balance between turbulent diffusion of heat downwards and upward advection of cold water. So we're going to write down the conservation equation, first for the temperature, and see what we get. So the flux, G, right, is going to consist of two parts. One will be an advective flux. So W is the vertical component of the velocity. So if V is the velocity, right, it has three components, eastward, northward, and upward. Right, so we take the upward component, because we're just going to do a 1D balance, times the temperature, and in fact we'll use the potential temperature, because it's more conservative, or the conservative temperature if you like. So this is the upward flux of temperature as the water flows upwards, right? So imagine a section somewhere, I don't know, maybe over here somewhere. I'll take a box, and there'll be upwards advection, W times theta, and then balancing this, there will be the downward diffusion of heat. Now the diffusive flux is a parameterization for the net effect of eddies, and if the eddies are overturning, they will mix heat downward only if there is a gradient in temperature, right? So if you have an eddy that's overturning and the water is homogeneous, same temperature everywhere, then the branch of the eddy that's flowing downward carries water at the same temperature as the branch that's moving upwards, and there's no net transport of heat. If, on the other hand, the water is warm above and cold below, then the part of the eddy that's flowing downwards is carrying the water from above downwards, so it's carrying warm water down, whereas the part of the eddy that's flowing up, it's bringing the cold water upwards, so it's carrying cold water. And the net effect is you have a mixing of heat from warm water to cold water. And so it's going to be proportional to the gradient of the temperature. And so it'll be proportional to, I'll use the red marker for the diffusive flux, d theta dz. And it's proportional to that, so there'll be some proportionality constant that I call k. And it's going to be down gradient. In other words, the heat flux will be from warm to cold, right? It's mixing the warm water into the cold water. So we need a negative sign, right? Vertical advection carries temperature upwards. Diffusion carries it down the gradient. And this is the flux of temperature, the vertical component. So I'll just put a little z here to remind you that it's the vertical component. And if we write down the conservation equation that we wrote down last time, so that's d theta dt plus div dot the flux is equal to 0, right? If in the absence of any internal sources or sink of temperature, this would be, and this is the flux of temperature, of potential temperature. This would be the conservation equation. If we go to one dimension, then this will become d theta dt plus the divergence. The vertical component of the divergence is just d by dz, and the flux is going to be this flux, w of theta minus k d theta dz equals 0. All right, so this is the one-dimensional conservation equation for potential temperature. So the rate of change of temperature at any fixed position is going to depend on the divergence of the vertical flux of temperature. And the flux of temperature is, there's a part due to advection, due to the currents, and a part due to the diffusion. All right, so if we now imagine that we're in a steady balance, so we look on climatological timescales, and we assume that the temperature profile, whatever it is independent of time, then we get this equation. So if we assume a steady state balance, steady state balance, then the equation boils down to w d theta dz minus k d2 theta dz squared equals 0. So what I've assumed is that steady state d theta dt is a constant, is 0, sorry, well, 0 is a constant, but it's constant. W is a constant, so I could pull it out of the derivative, and k is a constant. So assuming w and k are constant. All right, to simplify things now, we're going to divide through by minus k. We'll divide the equation through by minus k, make things easier, and we get this equation. The second derivative of theta with respect to z minus w over k d theta dz equals 0. So this is the resulting equation. So there's one parameter in the equation. There was two, the vertical advection and the diffusion, the diffusivity, but they only always appear in the equation as the ratio. So the only parameter we have is this ratio, and I'm going to give it a name. I'm going to call it delta. So I'm going to define delta as W over K. And then the equation becomes d2 theta dz squared minus delta d theta dz equals 0. And then theta is a function of z only. So this is clearly, it's a simplified model. In reality, the temperature is going to depend on x, y, and z, and time also. But we're imagining that we're averaging or waiting on long enough time scales that the time dependence goes away, and also that we're just looking at a kind of a large-scale horizontal average so that there's no longer any x and y dependence. So we have a second order constant coefficient differential equation, which is easy enough to solve, and it has one parameter that we don't know. So the idea of Munk was then to try to look at data, look at vertical profiles of potential temperature, and try to estimate delta. Now what he really was after was both W and K. He wanted to know what was the rate of deep water formation, which you can get, if you knew that, you could get W, or conversely, if you knew W, you can try to infer the rate of deep water formation. And he was also interested in what the value of kappa was, because that gives you the effective diffusivity, or how much turbulent mixing there is in the ocean. But the equation gives him only one parameter, just delta. So what he then did is that he tried to find another equation, another conservation equation, and one that might help him separate W from kappa. And the property that he used was radiocarbon. So radiocarbon is going to have a conservation equation very similar to this one, but unlike the potential temperature, there are in fact sinks of radiocarbon in the interior of the ocean, because it's radioactive and therefore it decays. And the fact that we will have a sink term is going to allow us to decouple the W from the K in the equation. So let's copy down this equation so we can remember it, and I'll write down the conservation equation for the radiocarbon, a one-dimensional balance again. So first, let me write down what my temperature balance is. So for temperature, potential temperature, we have d2 theta dz squared minus delta d theta dz equals 0. And now we're going to do it for radiocarbon. All right, radiocarbon. All right, so first let's think about the flux of radiocarbon. So J, the vertical component, there's going to be two parts. One part is going to be the advection again, times the radiocarbon. So this is the upward advective flux of radiocarbon, the same W as in that equation, right? Because it's transported by the mean upward current. And then the downward diffusion of radiocarbon. So there will be a minus K times R. Oh, no, proportional to the gradient. K times dr dz. And now we're going to stick this into the conservation equation. So dr dt is going to be plus the divergence of the fluxes is equal to the sources. So in 1D, the divergence is just d by dz of the flux Wr minus K dr dz equals, and this time it's not 0, this time there's a loss term, and the amount of radiocarbon lost is proportional to the amount of radiocarbon atoms, so this will be minus lambda r. So this is the sink term, sink. And lambda is the frequency, the loss frequency of radiocarbon. So maybe you know what the half-life of radiocarbon is. It's about 5,730 years, right? So in terms of lambda, lambda is the folding decay, so we know that e to the minus lambda t to the 1/2, sorry, e to the, t to the 1/2, sorry, t to the 1/2, that should decrease, that's the amount of time it takes to have half the radiocarbon atom decay. So the loss term, or the loss fraction that is lost is equal to 1/2 when we put in t 1/2 5,730 years. And if we take the logarithm of both sides, we get minus lambda t to the 1/2 is equal to minus log of 2, or lambda is equal to log 2 divided by t 1/2. So this now is our second conservation equation, right? Lambda is known, k and w are not known. We're trying to find out what they are. If we assume steady state assumption, the time derivative goes away, and then our equation becomes, assuming again that w and k are constant, we get w dr dz minus k d2r dz squared is equal to minus lambda r. If I then divide through by minus k again, the equation will become d2r dz squared minus delta, right? If I divide through by minus k, this will be w over k, which is delta dr dz. And on the right hand side is equal to plus lambda over r, not lambda times r. And let me distinguish, I want to keep lambda, so let me put this one a lambda 14 here to make it clear that this is the loss frequency for radiocarbon. If we had another element that had a different loss frequency, we can put a different lambda. So lambda 14, and then this one, this lambda will be the ratio. So we'll have a new parameter, which will be lambda, which will be defined as just lambda 14 divided by k. Okay, so now let me copy my second equation up here. So the second equation we have is d2r dz squared minus delta dr dz. Same equation, except that now we also have a loss term, wr, where delta is equal to w over k, and lambda is equal to lambda 14 over k. So we have these two parameters, delta and lambda. If we know delta and lambda, we can solve for w and k, right? We can get k. K is going to be equal to lambda 14 over lambda, and w is going to be k times delta. So now we can go and get some data of radiocarbon, a vertical profile of radiocarbon, a vertical profile of potential temperature, and we could try to find out what's the delta and the lambda that goes through the data as best as possible. And that's what we're going to do next. Before I do that, I just want to make a small comment of how we would compare R to the radiocarbon data. So when people measure radiocarbon, the amount, the loss rates are very tiny, so the fractions that are decayed, so they typically measure it relative to some standards. So they have some standard, and then they measure the amount of radiocarbon in their sample relative to the standard. And since you get numbers that are very close to 1, typically what they do is they subtract 1 from it and they multiply by 1,000. So to compare our R to delta 14C, which is the data, so R, what we do is we subtract 1 and multiply by 1,000, and this is like what is measured, which is delta 14C. All right, so it's just an affine function of R. So you take R, subtract 1, multiply by 1,000, you get back the radiocarbon that is measured and reported in the database. All right, the next thing we need to do is to actually solve these equations as a function of these parameters, and then go to the computer and try to compare these to the data. All right, let's take a break here.